Okay, I see that nobody's moving, and that's a good thing because we have a power session that's coming up. And perhaps you can tell your colleagues that are sitting outside to come in the room. I'm Sotiris Bantas with Centaur and Hitia, and my co-chair, Gregory Dumenis. We will be chairing this session entitled Internet of Things and AI, with 4 very interesting publications ranging from weather forecasting for maritime to deep learning to edge AI applications, which is, as you have seen, is a recurring theme for this conference, and also an interesting application for with applications in photovoltaics. So that's coming up. Without further ado, Gregory, do you have any opening statements for?
Skip the opening statement.
Yeah, you're also a presenter. So we'll, without further ado, let's hand it to Gregory Dumenis. He will be presenting on a short-term weather forecasting for maritime environments, exploiting an ML-based model at the edge, from the University of Ioannina.
Hello, everybody. Also welcome from my side. I'm Gregory Dumenis. I'm assistant professor at the University of Ioannina School of Telecommunications and Informatics. I was not to present this paper. This is from Vasiliki Naskari, who unfortunately had a virus infection and couldn't participate. I'm a co-author of the paper, so I will try to do my best to present it. So, what is the background of this work? The background concerns the EFOS project, a nationally funded project, which was investigating the importance of maritime weather nowcasting, and especially the correlation of the electrostatic field variation with weather predictability. So from one point of view, we have the attempt to investigate how electrostatic field, atmospheric electrostatic field can affect or can be used to predict changes in the weather conditions. And on the other hand, how this can be applied to the maritime industry. And in maritime, it is very important to have both short-term local weather predictions, which may affect safety of shipping, but also short to mid-term weather predictions, which may affect efficiency of the shipping by, for example, alternate the route or the speed of the ship in order to avoid a storm that may cross its path. The outcome of the project was first a fully untethered weather sensor installed onto the ship. And you can see here the concept on the right. Let me just see how this works. So it's this one. Oh. Okay, anyhow. So on the right side, you see the concept of the sensor, which a part of being able to measure electrostatic field. Actually, on the left side, you can see a commercially available sensor installed next to the sensor that was developed in the project. And you can see that our sensor is fully autonomous, also employing energy harvesting in order to ensure perpetual operation. And this has been done in collaboration with the physics department of the University of Thessaloniki, and also with Demokritos, the sensor lab of Demokritos that was developing the tribo generator that was powering the system. So the side effect, let's say, of this development was the fact that this system was installed on an actual commercial ship, and we had about a year's worth of a data set that had not only the normal, let's say, data that are logged in this situation, but also the electrostatic field. So the focus of this study is to make weather condition predictions using dynamic models improve the accuracy of the dynamic approach over static, let's say, methods for training, and in overall to develop a predictive model with short memory capable of being able to implement it at the edge. Okay. So the data set that we use consists of the measurement of the electrostatic field and also traditional measurements like air temperature, air humidity, air pressure, wind, true speed, and so on. And all this, of course, is a time series of data properly timestamped. And together with the data that we log, we also log a parameter called weather condition. Okay? And this is something which is normally used in shipping. It just categorizes the status of the weather, sea and wind, in discrete, let's say, categories from normal sea state to a gale, let's say. Before going into the actual processing of the data, we had to pass by the fact that these are real data captured from real devices, and there is always problems with the consistency of the data set. So that was obvious to us when we saw the data, so we had to remove outliers, we had to handle missing data that were caused by interruptions in the streaming of the data, and so on. And of course, we had also to convert the categorical data that I mentioned about the sea state to numerical equivalents used also for interpolation. A preliminary correlation analysis showed that the electrostatic field had little to no correlation to the other parameters that were logged simultaneously. We did know at the point that that's an empirical approach from our side. We don't have domain expertise. So we use the data, let's say, as a driver to find what's going on. So what we did is we transformed a little bit the data set by first enhancing with derivative data, like, for example, for the atmospheric electric field, we also used features of the signal, like its power, mean value, variance, skewness, and so on. And then, in the original vector of the data, we also time-wrapped the weather condition. So we say, OK, we want to predict what the weather will be 60 minutes from now. Okay? We have a data set, so let's shift the weather condition by 60 minutes. And then you have a vector which associates your current measurements with what the weather was 60 minutes after your measurement. And on that data set, we performed training. Oh, I'm a little bit behind. Using a Rydell-based function model. Okay? And we also compared static approaches where we trained the model with all the data that we had at once, with dynamic approaches where we used a short memory for the model and we retrained regularly. And this is the results that we got. Okay? So doing a 20 minutes prediction after 60 minutes, let's say, gave us an accuracy of about 57%. In the x-axis, you see, actually, this is all the data that we had about here, I said. And in the y-axis, you had the categorization of the sea state from completely calm to a near gale. Okay? Of course, the severe weather events were relatively rare, let's say, in our data set. If we do a dynamic training, that means that we actually forget most of the data. We use only the very short history, like 2 or 3 hours from here, and do again a 20-minute forecast. Then our accuracy goes up to 77%. And if we do that for a shorter window, 15 minutes instead of 20, then the accuracy of the forecast goes up to 83%. That means that by just looking at what the weather was, okay, 1 hour or 2 hours before, you can predict with 83% accuracy what the weather will be an hour after now, which is what you would expect because weather doesn't change all the time, even if the ship is moving and so on, okay, because we have also to take into account that this is not a stationary measurement. The ship is moving into different directions. Also, byproduct, let's say, of that is that we found out that the electric field measurement has little impact in the improvement of the accuracy of the model. Okay? So that means that maybe it's not really needed. Okay? If we look at the results in terms of mean square error and mean square error and stuff like that, we see that they're acceptable, let's say. And actually, I'm out of time. One important thing to observe here is that this model, especially the dynamic model, is very lightweight. It takes only 10 milliseconds to implement in a normal PC. And of course, we have a very limited data set to train, so also the training period is very small. So it's very well adapted for edge and local implementation. So the conclusions is that dynamic models are more accurate and adaptable than static models. The implementation is energy efficient. And there is operational impact in the sense that if you can predict an adverse weather change, this is very important for the safety, especially if we're talking about small vessels. Okay, as you saw, our sensor is also quite small and self-contained. So the future work for us is to investigate explicitly the adverse weather nowcasting, where we showed that the logging of the electrostatic field, because actually the changes come from electrical impulses in the vicinity, like thunders and stuff like that, is more important and specific. And this is what we are doing in the next steps. So I think I'm done.
Thank you. Thank you, Grigori.
Thank you very much.
We may have time for one quick question for Grigoris Domenis. Anyone? One from me then. Could this have saved the mega yacht in Italy that sank in Italy?
Actually, yes.
It could have.
Actually, yes, because this is exactly, I can tell you the following. The reason that we started this investigation about the severe weather is exactly because we got a report from the captain of the ship, okay, which was, as the mega yacht in anchor outside Libya, okay, and within 15 minutes, the weather changed from complete calm to near gale. The ship was moved, okay, and the captain sent us a message because he knew that we were logging and tell us, can you see if you can find something that could predict that? Because my ship, because it was in anchor, was completely unprotected. Everything was open, exactly as they told that the mega yacht was. So if I had 10 minutes advance, I could spare time. So yes,
Button down the hatches. Yeah. Thank you, Grigori. So we're calling our next speaker, Mr. Fotis Philippou from the University of Thessaly, presenting on an edge deep learning for low capability devices.
Okay, hello to everyone. Okay, my name is Fotis Philippou, and I'm a PhD student of the Department of Informatics and Telecommunications from here, the University of Thessaly. I'm very glad to return to the Department of Electrical and Computer Engineering, from where I have graduated 3 years ago, and to present our paper with title Edge Deep Learning for Low Capabilities Devices. Okay. Now, the presentation outline, we will focus on challenges in Edge AI, how we can overcome them with model compression, the pipeline of our work, pruning and quantization, the results that we have extracted, and some conclusions and future work. Now, the challenges in AI, in Edge AI, are the limited computational power. All of us have known that a smartphone and embedded system has very limited computational power and some power consumption constraints. Also, the memory is limited, and there are real-time processing requirements. So here comes model compression, some techniques that help us overcome those challenges by pruning and quantization, low-rank factorization, and transferred convolution filters, and knowledge distillation. We have focused on developing a hybrid model with pruning and quantization Now, let's see the pipeline. We have focused on object detection, on vision. We have used, for start, a YOLO pre-trained model. Okay, and we trained the model to a host machine with a more powerful GPU than an edge device to avoid extended training time. You know, training time for these models can be 4 or 5 hours and more. Next, we prune the model where we unnecessary or less important weights from the trained model are removed. This process happens to the host machine and not to the edge device. And next, we move the model to our edge device. We have used the Jetron Nano, the version of 4 GB, and we quantize the model here by converting the pruned model that we have into a more efficient format that uses lower precision. And the final output is a hybrid model that is ready for deployment. Now, what is pruning? Model pruning refers to the act of removing unimportant parameters from a deep learning neural network model to reduce the model size and enable more efficient model inference. We have developed a pruning function that allows for immediate pruning of our model on the same machine where the model was trained, as opposed to performing this operation on the edge device. Our pruning function is based on the below algorithm. For each layer of the model, we check its type, and if the layer is conv to D, we continue to step 3. Else, we compute the LN norm. It's an unstructured pruning the whole process of the weight matrix of the layer by this equation. Next, we sort the elements of weights by their absolute values, and we set the smallest weights to 0 based on the computed mask. Next, we remove any applied mask to finalize the pruning process, and the pruned model is next returned. So I have a sim here how pruning works, and we see that unnecessary weights are removed completely. Next, we take this model to our edge device, to the Jetson Nano, and here we try to quantize it by converting the model weights and activations from high precision, like 32-bit floats, to lower precision, like 8-bit integers. We have quantized all models from floating point 32 to floating point 16 due to hardware limitations, and we can't go to lower precision to int 8, using the provided framework from NVIDIA, the TensorRT. The steps of this method are very simple. The model is first converted to an ONNX file, and next the TensorRT generates an engine file, which is the quantized model ready for deployment. So, the results have been made using the YOLO V8 model and 3 versions of it, the N, the S, and M, and using the COCO 8 dataset, which is a dataset that can detect about 80 classes from a single image. First, in the left side, we can see the MAP 5095, which is the average of the mean average precision calculated at varying intersection over union thresholds, ranging from 0.50 to 0.95. We can see that there is a slight drop in precision, whereas in the right side, we can see that the inference speed, the milliseconds, for a single image have been dropped. For the YOLO V810, we have around 7 milliseconds drop, and for the others, which are bigger models, we have a very much bigger drop. So, The conclusion is that we have minimal drop in precision, we have enhanced inference speed, and this hybrid technique can be expanded to any custom PyTorch model that uses a pre-trained version of YOLO. Just before 2 weeks, the newest version of YOLO has been released from Ultralytics, the YOLO V8. We have tested it and it works pretty fine. And about future research, we will see advanced pruning strategies, dynamic quantization, quantization-aware training, and more. Some sampling reference that we have used. And this work has been funded by the Greek-funded project Connected Smart Cities for Greece to program. Thank you. I think that...
Thank you for this, for staying on time, besides the interesting presentation. We may have time for one quick question. Yeah, go ahead.
We can detect, I will talk to you about the project that we are working on. We can detect from a smart city the traffic. We can detect the place of the cars where they have done something wrong. And we can also use it in more for more use cases, like in agriculture and etc.
Okay, thank you for this.
Thank you.
So moving on, we're calling Mr. Christoforos Kachris from the University of West Attica, who will be presenting on a comprehensive comparison of YOLO-based object detection in edge applications, a use case for free parking spots. I have to say, Christoforos, my kids are using YOLO in a much different context than you guys, but it's interesting that this tends to be a topic of interest here at the conference. So go ahead.
Okay. Thank you very much. Actually, this could be a good use case for the presentation that you presented earlier. So maybe we can check this technique, right? So in every application, especially in edge applications, the most important question first is which model to use, right? So in some cases, it's very obvious. In some other case, you need to do some design space exploration. So in these cases, we decide to do a design space exploration to see which model is best for the specific application, right? So every conference paper or every publication usually starts from a problem that you face. Maybe you have faced this problem that in large parking spots, in large parking areas, usually you have to make several circles to find an empty parking spot, right? And this is kind of frustrating, especially if it is in parking, etc., right? So we thought how we could use AI for this kind of application. And the idea is to have a camera and try to classify which are the empty spots and which are not the empty spots in a large parking area, instead of having sensors, but using a camera that would be much easier to install, right? So this was the main motivation, and of course to try to find which is the best model for this one. So we tried to make a proof of concept kind of thing, right? So we wanted to make an integrated system that consists of a device, a small device, that it will have a camera. The camera will feed the Raspberry Pi, in this case, Raspberry Pi 4, clocked at 1.5 gigahertz. And then it will present this information based on the processing that it is done. It will present this information in a LED display that it will be very useful for the driver when it enters the parking spot to identify, okay, now I need to move to parking 1 or parking 2, etc., right? So this was the main motivation. So we had to move to use a Raspberry Pi, OpenCV, the YOLO, and Node-RED in order to present this information in the display. right? So we use the Node-RED in order to create the user interface that it will have a streaming interface of the camera, and it will show the availability of the parking, of the empty parking spots, right? And now we are working also in the next version using this Raspberry 5 and Hilo AI acceleration. Right? So we want to make a comparison and see which is the best model, especially when it comes to YOLO. Right? So YOLO is the obvious use case, right? The obvious model to use. You want an object detection, you want to make it fast, and there are a lot of versions from YOLO started almost 10 years ago, and now we are, I think, in YOLO version 10. Of course, there are 10 versions, and for each of these versions, you have also the nano, the small, the medium, etc. Right? So it's not obvious to see which model to use. Right? So we had to do a design space exploration. So we started with the most obvious, the most popular version, YOLO version 5, 8, and 10. And because we are targeting an edge application, it makes sense to use either the nano or the small and not the medium or the large, right? So in this case, it is, we don't have to make, we don't need to have a high throughput, right? Even 1 frame per second is enough for the specific application. So we just want to make sure that we have a good accuracy in order to identify the empty spots, right? So first we did a comparison in terms of the precision and the mean average precision. So we obtained some very good results, right, based on the data set that we got from Kaggle, right? So we did the confusion matrix for both YOLO version 5 and YOLO version 8, and we tried also to find what it is the training time, right? So it is an important factor, right? So you don't want to wait, I don't know, 20 days in order to do the training, right? You cannot afford it also to train it for 20 days or 1 month, right? So you want to have a small training time. So in this case, the YOLO V5 is in almost 1.5 hours, it managed to finish, right? The second thing that is also very important, especially in edge application, is the model size, right? So again, the YOLO version 5, in this case, it's small enough. So it is small enough to fit in edge application, and the smaller it is, it can fit in lower cost devices and lower cost processors, right? So you need to investigate, you need to study also the other version, right? YOLO 8, YOLO 10. All of these have better accuracy, especially when it comes to small objects, but always you need to have in mind what it is your specific application, right? And of course, we cared also about the inference time. In this case, the inference time, even 1 frame per second or 1 frame every 2 seconds is enough, so we don't care so much on this one. But still, in this case, YOLO V5 and YOLO V8 seems to be the ones that provide the best inference time. Right? Also this one. And some optimization that we did, also presented also in the previous version. So when you convert it to ONNX, then you can increase a little bit the throughput of the system, not a bit, significantly, right? So this also helps. Right, so the bottom line, what we learned from this use case is that every use case is unique, right? Especially when it comes to edge AI application. So every time you need to make a design space exploration to see not only what it is the latest version of the model that we are using, but which model fits best for your specific application in terms of all these parameters like the model size, the training time, the inference time, etc. Right? So it's not obvious, especially in edge AI application. So you need to make a small study in order to identify the best version and which of this configuration makes sense and which of these parameters make sense, right? So this is what we learned out of this one. So thank you very much.
Thank you, Christopher. This looks like a very interesting use case for the city of Volos here. We may have time for one quick question. Anyone?
What kind of data set did you use to experiment?
We used a data set from Kaggle, right? So we took a data set from Kaggle that is parking spots. It is around 1,600 figures, images out of this one, and we trained based on this one.
Okay, so that was a specific, let's say, parking area?
Yes.
So,
from several parking areas.
Yeah.
From several.
But is there any comparison, for example, against using a pre-trained data set to identify objects or to identify cars and stuff like that?
Yeah. So that's why, good question. That's why we used YOLO in first, and then we trained based on this data set in order to make it more specific on this one, since it could recognize the cars, but it couldn't recognize the empty spots. So we trained this with this one.
Thank you very much. Thank you.
Okay, so last paper in this session, and a topic which is close to my heart because I'm using photovoltaic panels in my home. You never know when to clean them. And hopefully this will be demystified by Mr. Alexandros Tsagaropoulos, who will be presenting on computing the cleanness of PV panels. And he's coming from the Computer Center of the Physics Department of the National and Kapodistrian University of Athens, Greece. Alexandros.
Good afternoon, everyone. I'm here today to present you our work on computing the cleanness of the photovoltaic panels. Yeah. This is a cooperative work of the University of Athens, and specifically the Physics Department and the Digital Systems team, and the in-access networks. So let's start. It is a fact that photovoltaic panels play a crucial role in the production of renewable energy. However, their surface gets often covered by dirt or particles, resulting in reduction of their efficiency by up to 85%. Current maintenance practices follow a periodic schedule of 3 to 6 months. Of course, the maintenance schedule could change and adapt on demand on the photovoltaic panel's conditions. Our objective with this work is to propose a computing system that provides a neural network-based solution to assess panel cleanness. This system is specifically designed to operate on the edge. The motivation for our work is based on the need for an automated system to assess if the panels are clean or not. This is specifically true for remote locations, where operators could not access directly the PV plants. Additionally, solar irradiance systems assume that PV panels are clean. So, to make the predictions more accurate about the power production, we need to maintain them clean. The edge computing system we visualized consists of 3 components. First of all, the Raspberry Pi camera module V3 captures images of the solar panels and sends them via the camera serial interface on the Raspberry Pi 0 to W. There, the computation is hosted on an ARM Cortex-A53 processor running at 1 GHz. The choice for this system is used for its low cost and general availability, about $20, and high computing efficiency, since it runs by consuming no more than 1.75 watts of power. Additionally, the third component of the system is the storage power plant controller that communicates with the Raspberry Pi 0 to W via Wi-Fi connection. Now, let's delve into the methodology of our approach. Initially, we gathered 1,000 images from the huge dataset of the Jeep Solar Eye. But due to the low variability of the dataset, we also collected another 1,000 images from proprietary sources, forming a dataset of 2,000 images in total. We also extensively used data augmentation techniques in order to make our dataset more robust. Examples of those are random image rotations, image flipping, and cropping. We additionally utilized the trivial augment transform, which specifically aids image classification problems. As far as training goes, we used two training schemes. Both utilized a training, validation, and test split of 72/820. The first training scheme is a standard one, where the model is trained on the train split and evaluated afterwards on the test split. The more sophisticated training scheme is the k-fold cross-validation that ensures faster model convergence and prevents overfitting of the data. We additionally employed transfer learning, leveraging the pre-trained weights on the ImageNet 1K dataset. We just changed the classifier layer to output two logits and then a softmax function, activation function to get the probabilities. Because the ImageNet 1K dataset provides 1,000 classes. We just need clean or soil data panels. As far as neural networks, we use 19 of them, but a lot of them belong to the same family, such as shuffle nets and efficient nets. The evaluation criteria we used were accuracy and processing speed in frames per second. Now on to the results. The table gathers our top 4 prevailing models. The top performing model is a ShuffleNet V2X15 that achieved just below 94% accuracy and 1.6 frames per second. Other notable mentions are ResNet34, ShuffleNet V2X20, and EfficientNet B2. The images on this slide are correctly classified by the top-performing model, and at the captions of them, the correct classification class is contained, as well as the probability. The probability is a number between 0 and 1, and the higher it is, it means the model was more confident with its choice. The center is an image of a solar panel that is completely clean. The others are depict a solar PV panel. The left is a photovoltaic panel partially covered in soil, as you can see, and the right is two solar panels completely covered in bird droppings. All the images were classified with very high probability, as is the case with any correctly classified images. Looking ahead, our future work will focus in 2 main areas. We plan to install cameras at various PV plants around the globe in order to monitor, in order to collect many soiling cases, starting from soiling, leaves, dirt, pollen, bird droppings, to snow, ice, and many more. Additionally, we plan to enhance our system capabilities. We will offer user-defined cleanest thresholds while providing multi-class classification for a more fine-grained classification of the soiling cases. We will also provide real-time monitoring and alerting of the PV panel's operators. To conclude, our proposed solution offers a system to maintain PV panels clean. By automating this process, we specifically aid remote PV plants and also improve the power output of plants. Thank you for your time, and I'm now open for any questions you might have.
Thank you, Alexander, and your colleagues for this very useful work. Have you guys figured out a way to clean them easily? I'm just joking. Any questions from the audience?
I think you mentioned it, but I think I lost it. Which technique have you used for data augmentation? I think that's a very, very interesting thing, because you have this problem all the time that you have too little data, right?
Yes, of course. Well, we actually used the simple ones like random image rotations, cropping and flipping of the image. And the other one was an established paper about trivial augment transform that specifically age image classification problems. For the other kinds of problems, it's not so fine-tuned. The results are not great, but specifically for image classification, you just provide how much you want the effect to be, how strong you want the data augmentation to be, and you just apply it, and they get you a data set with the same statistical probability, statistical characteristics, but very enhanced.
Okay, any more questions? Please.
So you have mentioned that you have built several architectures for neural
Mm-hmm.
networks. So why do you actually need them instead of just using, let's say, a golden image or a normalized version of the view of the panels and just do something very trivial, just like subtraction of the frames and detect the foreign particles?
To make sure I understand your question, you asked me why we just didn't use some specified model or 2 of them, 3 of them, and we tried 19 of them.
No, imagine you take an image of the,
Uh-huh.
of the photovoltaic panel, right, which is clean,
Yeah.
and then you compare it with the current state of the panel. Just by using a very trivial operation like subtraction.
Mm-hmm.
So the foreign substances should appear as the difference between the 2 frames. Why don't you do that?
Well, that's actually a great suggestion, but we hadn't prepared the data as such. We haven't yet installed globally cameras so as to get the specific panels we want to monitor. We just collected data from various Google sites or from Deep Solar Eye dataset. And a lot of times we hadn't got the reference level of, that is the clean panel. And another time, this is the soil case. So we couldn't do that. But actually, that's a great suggestion for our future work, when we will have installed cameras and we could do that kind of difference.
Yes, in practice, you will have this information available. What you have done here is more like an academic research.
Yeah, that's actually what we do.
Okay.
But if I may add, because I'm a little bit aware of the impact of that, even if you take the image of a clean cell, you cannot account from the beginning about, for example, variance in the inclination of the sun. So something that looks clean in the summer doesn't look clean in the winter, even if it's clean, because there is a different incidence. So again, you have to do some training to have his results.
Normalized, let's say, model to account for those.
Yeah. So then you have to do this. You have to do this for every plant you do the installation. But here they have a generic data set. You can even take an image with your smartphone and ask the system if it's sold or not.
Yeah.
When we get more specific, this could be a great suggestion, actually.
So I guess the answer is it's not practical to have one golden image that works across all panels in all situations and weather conditions. Thank you very much, Alexander.
Thank you.